Yeah, I've been noticing a lot of the Google and other folks have these really concise titles, so I still have a lot to learn, but sometimes fractal and sometimes quantum, blah, 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 basically universal representations in neural nets. I think I'll start with just a little bit of backstory here, that my background is basically in theoretical physics, and more specifically, physics of information, where I've been thinking about things like quantum information. What does it mean to predict the future from the past as well as possible? What's the relationship between energy and information, things like that. Specifically that question of what does it mean to predict the future from the past, that's kind of, in a way, the story of physics. Like, we wrote down equations of motion, chaos theory threw a wrench in that, but we kind of figured that part out a little bit. When I was doing and finishing my PhD, neural nets weren't that big of a deal. So of course I was like aware of them, but it's like we're doing the principled things and those are messy, so I could safely ignore that. More recently, obviously, the success of neural nets have kind of shaken my, principled, oh, that's the messy thing, right? It's like, okay, well, they're successful. There must be something to it. So I became convinced that it's an important problem to work on. And I thought there must be something about kind of the general theory about prediction playing a role in neural nets. So that's really been my trajectory in the last year or two in pivoting towards what I'd say is like a theory of neural nets. And it's gone surprisingly well. I hope you'll agree by the end of the talk. So it's encouraged us to start a new research organization, Simplex, where we can scale these insights, build a team to make this stuff happen. So how do we start? Let's start with a simple question of what can you learn from next token prediction, right? This is the prevailing training paradigm where you have some sequence of words that you tokenize and you just train the model to get the distribution over the next token right. Seems like that shouldn't work very well, yet here we are with our ChatGPTs and all this that seem to work amazingly well, and so that induces Twitter fights and whatever else it might be, these long poetic monologues on in discussions, but it's a lot of philosophizing without a deep understanding, and so what I hope that we'll get towards today is like, we can just do science to answer this question. Where's the theory? Where's the experiments to say what you learn from next token prediction? That's the goal. So to get there, it's a bit of a roadmap. I'll give some background. I probably have too many slides of background, but maybe this helps you to see where I'm coming from, how I am coming at this problem. Maybe it's a useful framing of thinking of kind of the implicit dynamics of moving through data in context. And then the correlational structure of data itself induces behaviors that we can anticipate for any intelligent system trained on it. And the two main things I want to talk about here is that it induces universal representations. So basically independent of your neural network architecture, the structure of data is going to tell us about universal representations. And then there's this kind of weird, sounds like crackpot stuff, but it's real. We're finding also that neural nets learn concise quantum and even post-quantum representations of classical data, which I don't think we would have known to look for if we weren't doing the theory. So what do I hope for you to come away with at the end of this? I hope that you'll come away with the answer to, what do you learn from next token prediction? With a little more confidence in the answer that, yeah, next token prediction is enough to learn a world model, but actually it's even more than that, because we're not training models to just generate data and act like a human. We're training them to predict data, right? And prediction is in a rigorous sense, prediction is a more difficult task than behaving a certain way, right? So we're talking about a certain probability distribution over tokens. Prediction is more difficult than generation, okay? So this is already a superhuman task, and it's kind of interesting when we think of like the Turing test of like, oh, well, no, this thing is sentient when it behaves like a human. Well, again, it's doing more than that. It's predicting humans. That's already superhuman, right? Next token prediction implies long horizon prediction. Basically, to do as well as possible at predicting the next token implies that you need to be able to get the correct probability density over the entire future when you condition on your past. And I've basically already mentioned this, that the intrinsic structure of data is going to tell us about behavior and internal representations. And hopefully, this brings a lot of excitement, and you guys will want to work on this. So yeah.
So your first bullet point, which architecture do you have in mind? Because, for instance, transformers can't learn world models, actually.
Yeah, so my claim is that there's basically architecture independent, more or less sort of thing. By the end of the talk, if you still have the question, let's revisit it.
Just to understand the claim. You're claiming transformers do learn accurate world models.
Transformers do, and I'll show that, and we can talk again later. Also other architectures, but transformers, yes. Okay, so we're training models to predict future tokens from past tokens. Let's make sure we're on the same page about what this means. So we have these transformers are the prominent architecture these days, or something like transformers. And there used to be the paradigm of you have some labeled data set, blah, 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 but that's hard to find data. This kind of clever thing where you have self-supervision, where you just take all the text on the internet, whatever, and then it's self-supervised in the sense of the stuff at the beginning should tell you about what comes next. So you don't have to hand label everything. It's already there. The task of prediction is a clever way to provide the self-supervision. So what do? You go into ChatGPT, you type in your prompt, and basically this thing gets tokenized to first order. You can think like every word becomes a token. And these tokens, so here I say, hello world, can computational mechanics help us to understand AGI? Computational mechanics, by the way, is just kind of this niche part of physics that I come from, which is built off chaos theory, information theory, talking about prediction. So these words become tokenized, which means they become integer representations. Those integers get embedded into a vector space. And then linear maps, nonlinearities, and out pops the answer. Obviously, we know the model's architecture. I mean, people design this stuff. But then you cram it with data. The weights of the model change. And then at that point, you don't really know. Like, we basically don't know how transformers or other neural nets work, despite all the hard work in this room and elsewhere. Even it's similar to, we know the rough architecture of the brain, but we don't really know how it works. So this is the goal, right? How do we bring light to the black box? So what I'm going to suggest is we focus on the dynamics of through context. So I'm thinking of this sequence of words, a sequence of tokens, as a sequence of correlated random variables, right? So each token, basically, I can think of as this random variable x sub, basically t for the time, if you want to think about it time-wise, but or just context position. So I have a correlated sequence of random variables. What can we do with this? Well, let's just ask some very basic questions of how random is this sequence? How predictable is it? How would I actually do the prediction? Right? Well, if I start thinking about probability distributions over sequences of kind of arbitrary length, let's say length L, then somehow this joint probability distribution over all these tokens has the answer. How I would suggest thinking about it is basically all the text that you're training on is sampled from some kind of Platonic truth out there. Okay, I think this will get us pretty far as an approximation. So there's something like a joint probability distribution that exists out there. And if we take that seriously, we can answer these questions. Just a bit of notation, I'll say like x sub 1 to L. So that's including every random variable, every token from 1 to L. This, of course, has this kind of decomposition. Right, so this has the answers, and as I've already said, then something about universal representations. Let's start with how random is the sequence, right? Well, you guys all know basic information theory, so you know it has something to do with the Shannon entropy, right? Shannon entropy, H, is just the sum over minus p log p, right? It quantifies how much information is in a random variable. And you can draw these bubbles, like the entropy of x corresponds to the area in the circle. When you start talking about joint random variables, it's kind of useful to think about a bit that basically the way that the chain rule for probabilities gets inherited, multiplication goes to addition for entropy. And I can think of like the entropy of y given x is going to be this crescent here. The mutual information between x and y is their overlap. So you can kind of build up some intuition this way. OK, but I'm not talking about the entropy of a random variable. I want to know something about this sequence. So the right question here is to say, what's the uncertainty or the entropy of the next token given that I've seen a length L history, right? So conditioning on your history, you're left with this crescent of how inherently unpredictable the next token is, even if you take all correlations into account, right? And if you had a stationary stochastic process, this would then asymptote to the Shannon entropy rate, the ultimate compressibility, right? Right, OK, so this is intrinsic randomness. You can't ever hope to predict this stuff, right, better than chance. So we've kind of answered this, how random is the process? Well, how predictable is it? And I want to emphasize predictability is not just the absence of randomness. It's actually an orthogonal question. So how predictable? Well, what do we mean by that? We mean how much of the future can you predict from the past? Pictorially, this makes sense. It's just the overlap of the past and future. It's the mutual information between past and future, right? That's how predictable time series is. OK, well, then how much memory do I need to predict the future? And well, you might say, well, come on, you just showed me. This is how much. Actually, this is kind of an interesting point. Is actually you in general need more memory than that. You need to remember more about the past than the past contains about the future. So there's kind of a funny thing about the minimal sufficient statistic of histories necessary to predict the future as well as possible is in general larger. So this is kind of one of the senses that I was saying, that prediction is harder than generation. If you just want to generate the thing, you can use less memory. If you want to predict the thing, you might need to hold on to more of the past than you might naively think. OK? So OK, here there's all these quantifiers, but how do you actually do the prediction? It's, of course, a much harder question. And I'm going to give some high-level version of this first. Of somehow we need to compress the past, right? There's too many different pasts. There's even with a finite alphabet, the number of possible paths is growing exponentially as you take longer histories. So what are we going to do to compress the past? Well, there's kind of this, in hindsight, obvious mantra that we can follow of don't distinguish paths that don't distinguish themselves for the purpose of prediction, right? So just coarse grain those. OK, well, the mantra can be kind of mathematized, formalized to be an equivalence class. So we can have an equivalence class over two histories, x pass and x pass prime. They're equivalent for the purpose of prediction if, well, this is just what we meant, if they induce the same distribution over possible futures, right? So then we can think about what I'll call process states, which are, you can think of either, they are the different conditional distributions over the future, or you could also think of them as they are collections of histories that are all equivalent. Mm-hmm. Right, so does this kind of make sense? OK, so some examples. So if I had very simple generators of stochastic processes, Like I have a fair coin. What about the past do I need to remember? Well, every history is the same, right? So I'm just flipping coins. I don't even remember anything. So there's one process state, and everything gets clumped there. So a biased coin is the same, right? Okay, it doesn't matter, right? Any IID process, there's a single memory state that you need. Well, nothing at all. If you have a Markov process, okay, a little richer, you need to remember the last thing that happened to predict the future as well as possible. You can have some larger order Markov process where you might need to remember more of the history. Here's a fun example of the even process where the parity matters. You can only have an even number of ones between any two zeros. And even though you just need to remember the parity, you might need to look arbitrarily far into the past to know what the parity is. Parentheses matching. You need to know how many parentheses have been opened, right? So this just kind of gives a hint at what sorts of things these equivalence classes are. But then there's also a dynamic over these as you observe more context. Right, so you can think of, okay, I'm in some distribution over the futures induced by the past, and I observe a new symbol with some probability p, and that would take me to a new distribution over futures. This is just kind of an explicit Bayesian update graph of moving from one belief to another. Right? So does this roughly make sense? I'm probably going more slow and should go to the representation stuff.
Well, just because you know all of these probabilities in order to define this equivalence relation.
Yeah, I'm giving myself way too much, right? I'm saying you have these probability distributions, and then maybe the answer is obvious or easy. We're of course in the regime with machine learning that you don't know. Like that's the hard part. But I think it's useful to lay out what would happen if you did know the joint probability distribution over all the tokens. Then what would happen? Okay, then we can back off and say we don't know it. Right. So to give something a little more concrete, I'm going to introduce hidden Markov models a little more explicitly as generators of structure. And then also they end up being kind of this answer to the metadynamics of beliefs. So let me just introduce this. So a hidden Markov model you can think of as a set of substochastic transition matrices and initial distribution over the hidden states. And basically just notationally, you would move from one state to another according to the elements of this substochastic transition matrix, which is a conditional joint distribution of if I'm in the state S, then what's the joint probability of observing an X and moving to the next hidden state S prime, right? So you can see these things graphically if you want. And if this was a stationary stochastic process, well, even if it wasn't actually, then you'd have the sum of the substochastic matrices gives a stochastic transition matrix T. This has a right eigenvector associated with eigenvalue 1. We can say, let's say, this thing's row stochastic. So if you sum all the rows, like a column vector of all ones, if you sum all the rows, you get 1 back. So that's the eigenvector 1. There's also a left eigenvector, which has to do with the stationary distribution. There's always some stationary distribution over this thing. And for a stationary stochastic process, that initial distribution would be that thing. One thing to note here is that the left and right eigenvectors are in general very different, which for a physicist is a bit sad that you need to treat left and right eigenvectors quite different. But there's actually a beautiful spectral theory that you can use in this more general context, which I'll come back to in a bit. Okay, and this is really where kind of the magic comes from, is that we can, if we allow ourselves this representation class of hidden Markov models, then we can calculate probabilities over any word, any sequence of tokens, just via linear algebra, right? Whatever your initial distribution is, you can think of this as a row vector, times a sequence of transition matrices, and then you just sum up probability. And that tells you the probability of a sequence of tokens, right? Now you might think, okay, well, this is a very limiting class. I know the Chomsky hierarchy. I want push-down automata, all this stuff. If you allow yourself infinite state hidden Markov models, you can actually produce any stochastic process, so it doesn't really matter. In any case, this is a useful toy. Right. Now, what about conditional probabilities? So the probability of a future given a past W. Well, I can just say that's the joint probability of history W and X future divided by the probability of W, right? Nothing crazy here. But then look at this thing, the thing in parentheses. So this is now some vector that hits the future. And any word W, any sequence of tokens that induces this same vector will make no difference on the future. It has no way of making a difference on the future. So this is kind of nice. Already there's some geometric intuition here. And words that induce similar vectors will somehow be close by. They'll affect the future similarly, right? So this is hinting at something useful. And there's, of course, the metadynamic among these belief states, these vectors. This is, again, the explicit graph of then your belief states. And Bayesian updating basically on your beliefs in linear algebraic form. Okay. So we're finally coming back now to this generation versus prediction. So there's this two-state hidden Markov model that can generate a process. But if your task is to predict it, then you have to keep track of the probability distribution over this. And a probability distribution over these states induces a density over all futures, right? So if you make that explicit, then this is what happens. Green are transient belief states. The blue-purple are recurrent belief states. And this thing kind of unravels. There's this property of non-unifilarity, which is if I was in this state and I saw a 0, I don't know which state I go to next. So when you do Bayesian updating, it kind of splits the probabilities in some sense, which is where this kind of these infinite number of states comes from. So let's look at this for a few examples of I have a generative mechanism of a biased coin, anything IID, well, whether the metadynamic or this mixed state presentation, there's just one state. Nothing clever to do there. If you have any Markov process, after one time step, you completely flush out of the transients. You know where you are. You know how to predict the future. If you have some finite Markov order, then you'll be in the transients up to the Markov order, and then you're completely flushed out. I think it's interesting that the transition matrix for the belief metadynamic is necessarily non-diagonalizable here. So it forces you to use interesting spectral theory. And then here's this even process I was referring to earlier that between any zeros, you can only see an even number of ones. So if you haven't yet seen a 0, you're going to rattle around in the transients until you find your first 0, then you're synced up. And this thing has the property of unifilarity. If you know what state you're in and you see a sequence, you know where you're going. For that reason, there's just a finite number of belief states here. More detail. OK. And then the last example I'll give on this is if you have non-ergodic processes, even very simple ones, you get very interesting belief update structures. So this is the idea that if you pull a sequence out of your bag, you maybe aren't sure which process it came from. Maybe it came from this generator with probability Q and this generator with just a different bias, probably 1 minus Q. And then figuring out which process you pulled the sequence from requires a pretty intricate belief structure, even if you have very simple ergodic components. I think that's worth keeping in mind. OK, what does this have to do? Anything with machine learning? Let's start getting back there. So we're training on this next token cross entropy loss. So you have your weights, theta, and you're looking at minus log probability of the next token given the past. This is what the model would say you should predict. This is the distribution given by the model. And then, of course, you're weighing each of these by what actually happens, by the real world Q. And if you do well at training, the weights will converge basically such that Q and P are the same. And then this cross entropy loss becomes just this, what I was calling the myopic entropy of the next token given some length past. And how is that achieved? Well, as we've seen, kind of the most obvious way to achieve predicting at this minimal entropy is to have a model of the world and to do Bayesian updating or something like Bayesian updating over that model of the world. That's the obvious thing to do. And in fact, empirically, that's what we find that transformers and other neural nets do. For a recurrent model, it had to be that way. For a feed-forward model like a transformers, it doesn't seem like it need to be that way. But there must be something like an inductive bias where this is the natural things for model to do. OK, so I'll quickly comment on how this leads to something like in-context learning. But are there any questions on this? No, OK. So I mentioned non-ergodicity as being important. How do we see this in language models? You'll see maybe the text says like blah, blah, something, something, Mr. Dursley, or blah, blah, something, Mr. Wonka. And then there's this idea in interpretability of these induction heads where if I've seen Dursley, then I'll probably see Dursley again. And you can think about that with reference to the structure of data. Induction heads are important when your data is non-ergodic, right? Because that then allows us to hone in on this. I'm probably in something like this ergodic component. Even if you knew which ergodic component you're in, language is very non-Markovian. So here's this example of what we call the random XOR process. You flip a coin, you flip another coin, and then the next token is just the XOR of the last two. And then you continue. Flip a coin, XOR of the last two. Okay? But you don't know the phase. So this is the generator. So even if you've learned the generative mechanism for the world, but you go to bed, you wake up, you start seeing things, you need to now synchronize to the latent state. So this is the explicit belief state metadynamic, which I've kind of laid out with its various symmetries here. And then the myopic entropy rate, the entropy of the next token given some history, is necessarily converging as it sees more context. And this thing can be calculated from the transition operator on the beliefs. So W is the transition matrix for the belief metadynamic. And so this, I'd say, like a kind of cartoon of in-context learning that models will synchronize to you, or they'll synchronize to the hidden state of the world in context, could be, in principle, calculated from the transition operator on beliefs, right?
You say language is non-Markovian. What do you mean by that?
When you say a word, the context matters. I can make better predictions if I remember more history than just the last word you said. Right?
I guess I'm not sure what Markovian is.
Oh, a Markovian process means that you can predict as well as possible just using the last token.
Oh, I see. So if it's like a order 3 Markov chain, that's not Markovian.
Sure, yeah, but I would also say that language is almost certainly infinite Markov order, just because there's simple structures that induce that. OK, so then for any finite state object here, this would imply something like exponential decay. But in fact, empirically, we observe power law decay in the next token entropy, basically the next word given passwords. And this can be explained either by non-ergodicity or something like a context-free grammar. In fact, we have both in language. So both of these will contribute something to the power law behavior of, well, in context learning. OK. So I want to move on to representations. OK. Everything we've talked about will be useful framing. But what we want to do now is to move from this kind of graphical structure of beliefs to somehow a geometric embedding of them. Right? And so this will be describing this paper you can find on the archive, which was recently accepted to NeurIPS. But before then, it made a bit of a splash on the internet, I think in part because we found fractals in the mind of AI, and that was exciting. But I think maybe a deeper reason that it made a splash is it was making a serious comment, kind of rigorous commentary on what it means for models to have, for machines to have a world model, and how that plays out in practice. And Adam Shai has done the bulk of this work and has done really an amazing job. It's been a great team to work with. So I'll try to sketch out what we anticipated, what we found here. So back to a toy hidden Markov model. This is just a 0-1 random process. Okay? We already talked about how you could build up an explicit graph of your optimal beliefs. Right? You just do Bayesian updating given some initial distribution. As you make observations, you synchronize and are able to make better predictions. OK, but now we want to move to an implied geometry. Well, you can think every distribution over these states lives in a probability simplex, right, over these states. So there's a 2 simplex where every belief is a distribution over the hidden states of this model. Does that make sense? So I have maybe my initial belief state, and as I observe, I'll bounce around in this simplex. But this is a bit funny, because I was just training on 0s and 1s. In no sense did I see this, me being the machine now. I didn't see this graphical structure. So how did I know to do this? Well, there's some universality that we can see that when the belief states, when these distributions have a certain structure, they just have a certain linear structure, that a linear combination of these 2 belief vectors gives this other one, that induces the same linear algebraic structure on probability distributions themselves. So really what we're getting at with having basically any generative model at all is that the belief geometry that it induces is universal because there's a certain linear relationship between or among conditional probability densities over the future, right? So that's what we're getting at. Right, and then how about finding these in models? So for a transformer, this is just a cartoon of a very standard transformer architecture. We call this the residual stream, and you can think of the transformer as kind of going off in branches where you have attention, MLP in these layers. And then you can think for any input, for any sequence input, it'll induce some point in the vector space, for your neurons here. So an input induces a point in your vector space, given the weights. Plops a point. So this is, if we look at all the different inputs, there's some, I guess, geometric structure. It's just whatever you end up finding there. And then what we claim is that there's just a linear projection of where all these inputs map to. There's a linear projection in which you're going to find this geometric representation of beliefs over the future. So this is just a cartoon here, but then this one is not a cartoon. Here's our random XOR process. This is a projection of the belief states, where I think it's important to note that many different belief states here have literally the same distribution over next tokens. We look inside the model, and we see that indeed, it chooses to represent these belief states, and it distinguishes beliefs over the far future, even if they have identical next token probability distributions. right? So then here's just another example of that. Here's a different three-state hidden Markov model that would generate the data. Now you would go back to the beginning of this presentation and you would say, do machines learn a model of the world? You might, even if you said yes, you'd say, well, yeah, it probably learns, it has three states and some transition probabilities. But our claim is much more specific. We're saying, actually, in the residual stream, you're going to find a linear representation of this kind of crazy fractal. Not just the components of this thing, but the beliefs that you would have if you were using a model of the world to update your understanding of the future. And indeed, over the course of training, we find exactly that this geometry emerges. And then we, or more precisely Adam, has done very careful analysis of this to make sure we're not fooling ourselves. I could come back to certain parts of this if you want, but basically, for some processes, the representation is spread across the layers. For some, it's not. And we verify that it does get the geometry of the full future correct, but it does not represent the geometry that you would think of representing the next token. So it really is representing geometries related to the far future. Too bad Ida left. So, OK. I mentioned universality. So this isn't particular to transformers. In fact, we basically almost said nothing about transformers. This is an architecture-independent theory. So we found it in transformers, sometimes fractal, sometimes not. Has to do with non-unifilarity or not. But we also then find it in RNNs, so in recurrent neural networks. We expected this to be the case, but we hadn't checked. Like I said, there was some excitement about this work, so we hosted a hackathon on this. And there was like 8 or 9 teams around the world that came together over an extended weekend, did amazing projects, and wrote up small papers on what they did. So this guy, Keenan Pepper, verified that indeed you find the same geometry for our 2 example processes represented in the hidden state of an RNN. So that's promising. And this perspective helps us to understand certain constraints, like if you want to represent these beliefs of the future, and your generative mechanism had 3 states, then your residual stream would have to have a certain number of dimensions, right? So there's a lot we can build on with this, right? So I'd like to move to the quantum thing, which I think I have, 12 minutes or something. But it's probably really important if there's questions to discuss those now, because we're going to do kind of a, quantum version of what we did. Right, so maybe I can just ask someone to summarize what we found to see if we're synced up. Not too many volunteers. OK, so I'll try again. So the last section is saying that transformers, or really any neural network trained on X-token prediction, linearly represents a belief geometry about the far future, right? Yeah.
When you say far future, you mean like many tokens out, or what precisely do you mean?
Yeah, right. So in particular, even if different histories induced literally the same distribution over the next token, it would choose to distinguish those histories and geometrically place them depending on how they affect the future, however far out it is. Yeah. Yeah.
You're taking the weights of the last step in this network. Those are the things you're projecting.
Not the weights. It's not the weights of the machine, but rather the weights imply a map from input to a point in the vector space of like how the neural activity. So we're looking at the projection of activations, not the weights. Does that make sense? Yeah, that's right. So this is basically showing, for all these different inputs, the activation vector it induces. And then there's this belief geometry is linearly represented there. I mean that there's a linear map going from the activations to our prediction in the probability simplex. So the same linear map takes every input activation to the simplex.
I mean, in some sense, if you just look at the last layer of the thing, then of course it goes linearly. You're saying something else, right? Because clearly the last layer, whatever it is.
Oh, I'm not talking about like the unembedding matrix, and I'm not talking about the prediction for the next token. I'm talking about the, these are probabilities, again, related to the future that are not necessarily the next token.
Is there an equation which,
What's that?
is there an equation which represents what you are saying?
Yeah, indeed. I don't remember which slide, unfortunately. So actually, I'll get to it in the quantum part. So I think this will actually be reinforcing a bit. Okay. So this gives a more general version of what I was saying. And right, so it sounds a bit crackpotty, but again, it's true that we find neural networks leverage these nominally quantum and post-quantum representations of classical data. This is work with Tom Elliott and Adam Shai. So I'm excited to unveil this to you. So things are kind of preliminary, but we have we're just writing it up, and it's quite solid actually. So we need to start. Well, we don't need to. Let's start by asking, what is a physical state? Okay, so people in like quantum foundations or foundations of physics ask, what is it like for the world to be classical? What is it like for the world to be quantum? Or even, what if quantum's not the ultimate theory? What would it be like for the world to have a post-quantum state? Okay. Well, by classical, kind of the cartoon of this is you have some number of microstates, and the world is either in a microstate, or if we allow ourselves some uncertainty, then you can be in some, the convex hull of those microstates. So basically a probability simplex over microstates. So we think of like a classical memory system is basically a probability vector over some microstates. What is a quantum state like? Well, if you took any quantum courses, you probably came across this density matrix, which is a positive semi-definite self-adjoint trace one operator. And the big difference between classical is there's some kind of continuity between pure states, right? So like on the simplex, classically, there's a separation between pure states, but in quantum, you can move continuously between pure states. That's really the big difference. But there's still some restrictions on what it would be like for the world to be quantum and what it would be like for these quantum states to evolve. And so there's ideas of post-quantum theories where you just kind of relax those assumptions a bit in terms of what the states can be like and how they would evolve. So here's kind of this classical picture of points in the probability simplex. And then in quantum, you might have seen this block vector to represent the states of a qubit. A pure state for a qubit would be somewhere on the surface. And a mixed state, a probabilistic mixture with some uncertainty, would be somewhere inside of that sphere. Oftentimes, popular science does an awful job of saying, oh, quantum's different because you can be 0 and 1. Well, that's really bad because like that suggests, OK, 0 plus 1. Yes, that is a quantum state. But also 0 minus 1 is a valid and different quantum state. So really, linear combinations of basis states are the things that matter, right? Okay, and so here's how we're going to come back to classical stochastic processes and neural nets. It's been shown that there are classical stochastic processes that would require an infinite number of classical states, basically an infinite hidden Markov model. But if you allowed yourself a quantum physical system, it could produce the classical observations with a finite dimensional Hilbert space.
Does this come out of Kahn embedding stuff? Or
What do you call it?
the difference between this C and Q? Is this from like this Kahn embedding conjecture being false? Or?
I'm not. Yeah, I'm familiar with this work, but I'm not familiar with that way of thinking about it. Right. So this has been known. This separation between C and Q has been known for quite a while, for many decades. And just this year, it was also shown that there's a distinction between sometimes you would need an infinite dimensional Hilbert space, and obviously also then an infinite classical model to produce some classical stochastic process. But if the world was post-quantum, you could use a post-quantum physical state to produce this with finite dimensions. But so post-quantum, you drop some of the assumptions about like completely positive trace-preserving maps and things like that. Yeah. Oh, right. So this is kind of a funny thing. GPTs, generalized probabilistic theories. So now we find GPTs and GPTs. So this stuff, I've worked on some of this stuff, and then it's funny though, because okay, you say no classical, no quantum system could instantiate this physical thing, but then they write down in the papers, people will write down then these finite dimensional matrices, and that's like, this is the post-quantum physical state that does the thing. Well, that's confusing. I mean, if we're just talking about matrices, what's really not classical here? And one way to think about this is that the supposed advantages of these quantum post-quantum states is really that it's taking advantage of states living in a real-valued vector space. Well, neural nets are like this. So I had worked on this stuff. I'd worked on that simplex result, and then I convinced myself I guess many months ago now, that this is crazy. Neural nets must learn these quantum representations, supposedly quantum representations, because they have access to an effectively real-valued vector space. Because the neural activations are up to machine precision, just a real-value vector, right? So we checked, and that's indeed what we find. So I'll give a quick version of this. One way to think about transformation of a quantum state is via Krauss operators. So there's like a certain representation for how an open quantum system would change. Basically, if I observed an X. So there's the quantum memory system, and then there's some ancillary quantum states. And then you can basically measure the ancillary systems to get the classical output, but then the quantum memory rides along. This is how you get the advantage. Right? Okay, so how can neural nets do this? Well, this is just some linear superoperator. So if we changed representations, it would seem more obvious. And well, in the case of a qubit, you have this block vector. That feels more familiar. And in fact, you can just choose any traceless orthonormal Hermitian operator basis, and you can do this for whatever your quantum dimension is. So you just have this generalized block vector, which is linear representation of the density matrix. Okay. Right. So then we're back in something that looks a lot like a hidden Markov model, but we've relaxed constraints. And if you do Bayesian updating over the quantum physical system, you'll see, like for our example process where we write out these Krauss operators that induce these transition matrices. This is what your beliefs look like in the block sphere for an example system. You change the parameters a little bit, and you see this cool stuff. So the claim is that neural nets would also learn beliefs about the future as if they had a quantum world model, if that ends up being more concise for the classical stochastic process. There's some results like, oh, days of the week live on a circle, right? Maybe you've seen some of these results. So something about the quantum aspect might come in there. So we do the same sort of game where we train the model on just the whatever the classical tokens are. We say if the thing had, there's no finite representation of this classically, but if it had access to like a quantum representation, this is what its beliefs would look like. Over the course of training, indeed, we find that this is a transformer, that a transformer learns how to update beliefs given effectively what people would call a quantum model. So for interest of time, I'm just going to show a few examples. This is just a totally different quantum-generated process that has no finite HMM representation. And these are the points that we would say should be learned if it was moving all histories, the activation induced by all histories into this geometric representation. At the beginning of training, it's a big mess, but compare the left and right, and in the end, the transformer learns this representation of the world as if it was using a quantum world model to update its belief about the future. The generalized probabilistic theories, basically, you can write them down to make them look like hidden Markov models. Instead of T's, they're G's, whatever. Basically, I just relax that I can allow negative elements, but they're just linear transformations. You still use your kind of linear algebra in the same way to calculate words. That means that your conditional probabilities have the exact same thing, right? Where different words that induce the same vector have the same impact on the future, right? This is the equation, I think, Elvis, that you were looking for. What we anticipate is that the geometric representation of the different conditional distributions of the future induced by the past correspond to these vector elements. Right, and so these are the belief states that we find in transformers and other neural nets. And this is just, I think, a final slide to show that indeed for a stochastic process which would have no finite dimensional classical representation and not even any finite dimensional quantum representation, it should have this geometry for this example we look at. Okay, over the course of training, neural networks discover and utilize representations of nominal, a post-quantum representation. So we find this fun and also encouraging that we can say something about what the representations are. We can anticipate and then find what the representations are in neural networks, and it corresponds to the structure of data itself. In fact, these post-quantum things now, like, drop the physics. They're actually easier. They're easier to find even than an HMM or a quantum representation because the smallest HMM or the smallest quantum representation is actually a very weird convex optimization problem. So if you drop that, you automatically get the post-quantum representation, and that's what models find when it's more compact. So I'd say this is all very good news, that we're able to make these anticipations where we have some better understanding of what models are learning when we train them on next token prediction. And we're really encouraged by this and happy to build on this with other researchers that feel like they have some way to contribute. So if you are inspired, reach out. I'm happy to chat with you.